let me introduce the 4 key players in this game. Stress, strain, force, and displacement. And I think most of the things we do in structural engineering, structural mechanics is playing with these 4 people and the relationship between them. One is known, others are not known. We start from one point and it's a loop, it's a cycle. So for example, stress and strain is a constitutive law. Stress and strain, we all know basic law is there. The relationship between stress and force is stress resultant, like that. The relationship between strain and displacement is compatibility. And then relationship between force and displacement is equilibrium. So we have these 4 relationships, 4 that exist between them. So we can start from one, depending upon what is available, what is not available, and we can move around this cycle. But the problem is, many of these are only good in linear elastic system. As soon as things become nonlinear, inelastic, many of these relationships in the traditional sense will break down. And that's where the problems will start, and we'll have to update them. So we will keep coming back to them, time and again, these 4 players. So now that we have them, let's see, first of all, let's see force to deformation. Currently, it's easy. We have the equation for the elastic response, so we can calculate the deflection based on the linear stiffness and linear something, so it's very clear. We know the force, moment, we know the deflection, the formula is there, no problem there. But ACI, so this is the force and displacement, KU, stiffness equation, and from that relationship, we can calculate that. But immediately we have 2 different equations for the same deflection now. One deflection, one coming from the elastic response, second one estimated pseudo nonlinear response, which code is trying to capture by replacing the I and E by EC and IE. And both these are arbitrarily, and different codes will do it differently, which means if every code has different number, all of them cannot be correct. So which means all of them are wrong by simple logic. So which means that something is now missing in this part already in a very basic level. So let's go to the second one. This is very interesting. Load to stress to strain path. We think traditionally that if you know the load or the force, you can calculate the stress, and from the constitutive law, you can calculate the strain. Okay, and this seems obvious, and that's what working strengths design has been, and all of the design in the past has been like that. But let's see what happens. So this is a small, column. So we're going to go to applied load to go this way. We're going to load to analysis. In this case, simple analysis, member action, which is simple P, cross-section action, and then stress strain. Okay. So area is like that. Stress is equal to P over A. It's very simple. So if we do that, and I go to try to jump from the stress to strain, I need to go to the constitutive law, which is not simple E, which is a stress strain curve, which defines the whole path. So it's not just because the simple modulus of elasticity in our case. So if I do that, so if the stress is here, I immediately get an problem. Now I get 2 strains for the same stress. So which means the problem is no longer unique, because for the same stress, there are 2 possibilities of strains. And at some stress, there is no strain. So which means this is not a reliable way to proceed, because you are not sure of the outcome of this stress to strain value. Because first case, because it's no longer linear, the E is limited. So for certain stress, there won't be any strains available. And for certain stress, there might be two strains available, which means this is not a good path to follow, because it doesn't give you unique and reliable strain. So that means we must reverse this one. We should do the other way. So strain is non-existent and strain is non-deterministic. So we have 2 problems straight away. So let's reverse the thing, strain stress to load capacity. Now we have no problem. Because now if I do this one and I say, okay, I don't know the load, I don't care about that. I have a column on which the certain deflection delta has taken place, deformation has taken place, and I don't know what that is, but for that delta, there's a certain strain produced, E delta over L, and then for this strain, I can go to this one and I can come back to calculate strain, to calculate stress. So this is a unique solution now, that for every strain, as long as the strain is within the limit of the material, I will get a unique solution of the stress, and I can calculate the corresponding capacity from that, and I can get P max and PS one thing, and I can get the capacity. So which means a valid solution is possible. So this is what we follow these days for the purpose of investigation. Start from the material response, go back to section response in this case, and go back to load capacity. So we go material response, which is the stress strain curve, and then section response, which is the area, and this one, to member response, which will include the length and so on, and structural response and load capacity. And then we can check that load capacity against applied load to calculate the real factor of safety that is available. Is like summary of the pushover analysis, kind of, right? Because you calculate the real capacity, true capacity based on the material. So now if you have a particular structure to evaluate, you start with the material, testing material numbers, actual cross-section, actual thing, you can calculate the capacity very reliably, and then you can compare it with whatever loading that you want to compare and see it's valid or not valid. So this reverse direction works very well, and that becomes the basis of all of our further development. All right, so then we get the P from there. And for constitutive law, we know that the stress strain curve has all the information that we need. We have a stress strain curve with the stiffness, yield point, strain hardening, necking, fracture, and this can give you a lot of information about the material. For example, ductile, non-ductile, brittle, and all of that, and post-elastoplastic. So we can define all of that. We can define linear elastic. You can define linear inelastic, non-linear elastic, and non-linear inelastic. So you get 4 material response from there. Here, materials of different kind, materials of different type, deformation type, different relationship type. So stress strain curve actually gives you all of the information about the material response that you are ever going to need for the analysis. This stress strain curve can be modified by many things, and we will talk about some of them. So which means that if we have the stress strain curve of the material, we have a perfect starting point for our whole analysis that we did. You have the valid material. From that, you go back and calculate the capacity. So there's no ambiguity problem here, as long as we have tested the material and we have got the capacities. Second one is the cross-section. Let's also see how we can unify the cross-section, make it general, because a rectangular beam is not a good sample to start with, because the cross-section can be many. It can be reinforced, unreinforced, post-tension, composite. Many things will come up. We have, so many. So we need to make sure that we are able to handle cross-section, or general cross-section, which can include steel pre-stressing, general, like for example, carbon fiber or whatever, and concrete of any kind. So we put the material as a stress strain curve on one side as an input. Polygon, general polygon shape, not rectangle, made from any polygon to define the cross-section. T-section, rectangular, polygon, doesn't matter to us. And then we put the unified type of beam and column. You don't need to differentiate. We put 3 stress resultants from there, or 5, or from both sides. And then we put unreinforced, reinforced composite post-tension, reinforced every type of section, and put them all together. So this is a complete problem definition of a concrete structure of every type. Everything is covered. There's nothing outside this one. So if we take this as our starting point and say, okay, this is our cross-section, and then we can go ahead and deform it on a certain angular direction for a specified strain, any strain, starting with any strain, just like we did for the previous case. And then we say, okay, then we can come up with these equations for the equilibrium of the stress resultant. So we can integrate all the stress resultants based on that cross-section, based on the material stress strain curve here. This is a strain diagram, this one, this one. Now this equation has the ability to remove all of your typical assumptions in reinforced concrete design. Plane sections, no need to remain plane, no need to have 0.003 as the limiting strain known. So all the 5, 6 basic assumptions in the development of the strength theory or the design theory in ACI code, we can get rid of them all and develop an equation which doesn't apply on any one of them. And the same equation will apply to column, to slab, to footing, to post tension, to everything. Okay? Because we started with this cross-section is like that. Because no matter how many materials we have, we just keep adding them and integrating them. Each individual stress strain curve, we just adding that. So this is the equation that we now have, which becomes our starting point for cross-section level response to be determined from a general material that we defined. And so we can use that and we can plot them into this surface, and this becomes our capacity interaction surface for a given value of the material cross-section. So everything has to be known before we can generate that. This is not a good design tool because nothing is known. But for investigation, this is a perfect tool because everything is already existing. You know what material is there, what cross-section is there, what the distribution is there. So the evaluation will be perfect. This equation will serve perfectly for investigation. So that means now we have the tool to investigate the so-called capacity of the cross-section independent of, and there is no mention of the building codes here. This is true. But you can modify it for code. You can add phi factors here, you can add gamma factors here in this equation, and you can have the same equation for different codes. Just modify this by the appropriate phi factors and gamma factors. So now let's come back to, once again, to the basic problem and try to apply those equations and see where we can go from there. So come back to, again, the problem of a axial strain. So we have a simple prism with some axial strain coming from any deformation that we do not know, but we know that we are, so let's say we say, okay, strain is equal to a certain value, and from there, we have a cross-section that we define, and we can just now, just for the sake of convenience, we say that the strain is equal to 0.003. It could be any number, 3.5, 3.8, 2.9, doesn't matter. Just for the sake of convenience, we say the strain is equal to 0.003. And then from there, we can go to the stress strain curve and we can read two stress strain curves, one for steel, one for concrete now, because it's a composite section. And then we say, okay, for 0.003 strain, I'm going to read the corresponding stress from those numbers, and then I'm going to add them together by this simple formula, and I will get back the axial load capacity. So which means now the whole cycle is complete. Stress strain curve, cross-section, and the capacity are now interlinked. And this can be any strain, so we can read the curve at any strain level. We are not limited to the code specified limits anymore. So then that goes over there, and this goes over there. So which means that those equations on a simplet form can work in this way. And then we get the axial capacity resultant. Let's go to now the slightly more complicated problem of curvature. Not only axial load, but we assume that it's not just strain, but it's a curvature. So now the strain has a varying profile and it's not uniform anymore. So in that case, what will happen is that you have a beam that we talked about, you have a strain diagram that might look like this. Any strain profile will be fine. And from there, you have so you take this strain profile and you plot the stress strain curve on the cross section. Variation of the strain from 0 to max will actually get you the stress strain curve. You take that stress curve, plot the cross section, fill it up on the whole cross section, you get this volume of stress. And then you get the same thing, you get that, and you put this here. And now we have two things with the strain variation, each level strain and stress connected through the stress strain curve. And then we get that, because in this case there's no axial load. So with that C equals 0, actually P should be force here. So this should be another word. And then moment capacity now will come at. We integrate the forces in concrete, and we sum up the forces in rebars and multiply them by the corresponding arm. We get the moment capacity from there. So that becomes moment capacity stress resultant from that. So in both cases, we start with an assumed strain either a uniform strain or a strain profile, and we work out the corresponding stress. So that's now everything is connected, is clear. Let's go to now one more application of the same thing. I change the notation. So we apply axial load and we also have F there. Now it's no longer a simple beam, it's a column. I just put for purpose of convenience. So it's a column with axial force plus the bending moment coming from any reason. So same thing will apply, nothing will change. The only thing will change is that now the equilibrium must satisfy P is equal to CT, not 0 anymore, because now we have P. So we have to find that solution which satisfies this axial load presence, and then we find the moment corresponding to that, and we get the capacity. Now we can keep changing the orientation of the strain or the depth of the neutral axis so that the strain profile keeps changing. For every variation of strain, we can get one value of moment and one corresponding value of curvature, because curvature is equal to the depth of the neutral axis strain over depth of the neutral axis, or whichever way you define it. So every time you move the neutral axis down here, this KD, or change the strain value, you get a new curvature and you get a new moment, valid moment. So you just vary them and you satisfy this equilibrium of P is equal to CT, you get a valid moment curvature curve for this section, which includes the axial load and includes all of the nonlinearity of the cross section and of the material. So which means that we get now a nice, neat moment curvature curve for that section using that formulation. So now we have not one point, but all the points on the deformation line as we did for the real beam, which we remember we had that. So which means that now this beam can give you, this is coming from now CSI Call, another program that you can use, you have here, and you can use it for this project also. So on this one, I just compared the moment calculated by the eagle eye on that, and it becomes 1 point on that curve. So that means the design moment is one of the points on the moment curvature curve, but the moment curvature gives you all the points that you need to answer all the questions that we have from this beam to investigate. Because what we are looking for now is what is happening at each point. So each point you can get concrete force, compression force, tensile force, maximum concrete strain, maximum steel strain, neutral axis depth, curvature, status, neutral axis, everything. You have full information about the cross-section behavior at every point along the curve, because we didn't go the strength way, we came the curvature way, and we generate the moment curvature because we have drawn it from all possible variations of strain and neutral axis that give you a valid solution for this one. So this is a valid response of the beam cross-section from A to Z. So you can now study, you can get everything. So this different points give you all of the information from that. And that is what we are looking for, to how to get a full understanding of the beam that we were trying to do through its entire load history. Before cracking, cracking is here, before yielding, here, post yielding, this one, whatever you need, it is there now. Okay, and that's the advantage of going this way. Okay, and you can also see cross-section stresses, profiles, and plot by moving the pointer on anywhere on the curve, and you can just study what's happening with the strains and what's happening with the stresses in 2D, in 3D, and whatever. If you haven't done it, please try CSI Call. You can see all of that, right? So which means that theory that we develop now gives us the ability to get full understanding of the cross-section, especially for axial load and bending moment. And this could be single curvature, double curvature, whichever way you want to do it.